let us start this lecture with the thought process. A tiny spark can cause a mighty fire. So, in the last lecture we basically initiate a discussion how to derive a relationship for burning velocity by considering a one dimensional laminar steady flame, right, and we have made the assumptions, and I will just repeating some of these things, that is one dimensional steady inviscid laminar flow, and flame is quite thin, and no heat loss including radiation, ideal gas law can be used, single step chemistry model we will be using, and of course unity Lewis number and constant properties we will be considering, right. And if you look at what we will be doing, we will be basically looking at the all this mass conservation equations for our case, right. So, let us consider the mass conservation. Mass conservation equation for the one dimensional steady flow, what it would be? It would be nothing but your by dx rho Vx, if I say in the x direction only, right, is equal to 0, right, and let us say this is equation 1. The momentum conservation for one dimensional steady inviscid laminar flow, that would be rho Vx dVx dx minus dP by dx, because the viscous term is not there and it is a steady flow, right, equation 2. And species conservation, and we will be considering the single step chemistry, right. So, if you look at single step chemistry model, that is fuel is reacting with the new moles of oxidizer going to nu plus 1 of product, right. That means, I am having fuel, oxidizer and product, I will have to having I will have to invoke 3 equation basically. One is for the fuel is rho Vx, Vx is the velocity along the x direction, and the mass fraction of fuel dy by dx is equal to rho d square yf by dx square plus f, right. This is basically diffusion term, like mass diffusion. And this is your source term, mass for fuel, mass consumption of fuel per unit volume, and this is of course your convection term. Right, and this is equation 3. Similarly, oxidizer rho Vx D is the mass diffusivity. And the product will be rho Vx d product x is equal to rho d plus m dot triple dash product 4 is a 5. and similarly we can write down the energy equation. Rho Vx Cpt dx is equal to kg d square by dx square plus lambda I hf I naught, is not it? This basically I is equal to 1 to n, that in this case n will be 3, fuel, oxidizer and the product. And if you look at, if you want to solve these things, you need to have a boundary condition, right? What are the boundary condition you are having? That x is equal to minus infinity. Let me draw that, because if I look at, this is my flame x. So, my flame would be like, this is minus infinity, this is plus infinity, right. And if I take a maybe temperature profile to illustrate this point, right, it will be this is Tf, this is Tu, right. And what happens to here at minus infinity, the gradient, this will be dt by dx is equal to 0, and similarly here dt by dx is equal to 0. Here, yes or no? So, I can write down that this is basically infinity, t is equal to Tu, and dt by dx is equal to 0, x infinity, t is equal to Tf, dt by dx is equal to 0, right. And if you look at, like we will have to now consider how to, because these are coupled equations, right, and it is also non-linear in nature, because the term is, source term is the non-linear, right. So, what we will have to do, we will have to see that, simplify it, and let us look at the mass conservation by considering equation 1, that is mass conservation, right. What I can then, I can integrate that, and that is rho Vx by dx is equal to 0, that if I integrate it, equation 1, I can get basically rho Vx, right, is equal to constant is equal to mass flux, is not it? Mass flux remaining constant for one day, and that is equal to, if I say this is SL, right, that means this flow which will be taking place is basically nothing but your rho U SL, right, because the fluid which will be fuel plus air, in our case I am considering, or mixture, will be moving with what, same velocity that of the burning velocity. Are you getting? Then that is nothing but rho U SL, yes or no? So, this we will be using that later on. Let us say this is equation, if you consider that, this will be 6, I guess, right? Is it right? This 6, this will be 7. And let us look at the momentum equation. Momentum equation, right. Okay. by integrating momentum equation, that is 2, right, between station 1 and 2. Let us say I am saying this is station 1 and this is, let us say, station 2, something, you know, away. If I will do that, what I will get? I can get, this is, if I integrate this equation, what I will get? I will get rho Vx square, right, into the station 1 to 2 is equal to dP, of course this will be minus 1 to 2, right. I can write down that whatever we have done already, I think let me write down, that is rho Vx square, I can say 2 minus rho 1 Vx square 1 is equal to P1 minus P2, right. So, if I mean I have already done for when we are talking about detonation or when we are talking about combustion wave analysis, right. That is nothing but here I can say rho square 2 Vx2 square is equal to 1 by rho 2 minus 1 by rho 1, right. Can I not write that this, isn't it? Because I am taking rho 2 here multiplied by there, that things, right. And considering that is rho 1 Vx1 is equal to rho 2 Vx2 from the continuity, from equation 7. So, is equal to P1 minus P2. Or I can write down, this is nothing but your rho u SL whole square into 1 by rho 2 minus rho 1 is equal to P1 minus P2. We will substitute some values, right. So, how, what will be the difference between these two pressure between station 1 and station 2? Is it a very big quantity or a small quantity? Let us consider the for methane air laminar flame, right, and phi is equal to 1. I will consider SL as 0.4 centimeter, no 0.4 meter per second, basically 40 centimeter per second, 0.4 meter per second, and rho u I can take as 1.12 kg per meter cube density. I have taken air, but it depends on that, but it may be some order of that. Okay. Now, if you look at rho 2, which is nothing but rho 1 in this case, right, and rho 2 by rho 1 is equal to T1 by T2 from the ideal gas law, keeping that pressure is remaining constant, but for the time being. But now, what will be, this is, let us say T1 is 300 Kelvin and T2 will be adiabatic temperature I am considering, what will be that, 2200 Kelvin. Okay. If I consider that 300 divided by 2200 Kelvin, it is coming something 1363, and similarly the density 2 will be 153 kg per meter cube. Now, if I substitute this, I can say equation 8, substituting the values, the above values in equation 8, we can get, what is that, P1 minus P2 will be rho 1.12 into SL is 0.4 whole square 1 by 0.153 minus 1 by 1.12, you will get is a very low value, you will get, that is something 1.128 Pascal. And if you look at what is P1, P1 is 101,325 Pascal. As compared to the pressure, right, the P1 minus P2 is very small, is quite small as compared to P1. If I take atmospheric pressure, if I take higher pressure, it may be little bit more, but however this is very small. Therefore, pressure, it implies pressure remains constant across 1D steady laminar flame. Therefore, there is no need to consider the momentum equation. Momentum equation is basically turns to be 0, right? Yes or no? If I say, that means my momentum equation is rho Vx dVx by dx minus dP by dx, and this happens to be 0, right? There is no need really to consider, but change in pressure is across the x is very 0. So, this is 0. So, therefore, there is no need to consider the momentum equation. So, what we will be now considering is basically we will be considering the energy equation and finding out a relationship for burning velocity, right. So, let us now write down the energy equation. Energy conservation equation. This is equation is what number? 6. As I can write down this as Cp I am taking out, because Cp is a constant, we are considering constant properties, right. So, dt by dx is equal to kg dt x by dx square plus summation of m dot triple dash I So, this equation we need to basically solve it, so that you can have relations for that, and keep in mind that m dash is equal to nothing but rho u SL, that already we have derived. Now, this is basically a second order non-linear equations, right, and it is having two unknown. This is a second order non-linear equation, OD, ordinary differential equation, right, and it is basically having two unknowns, right. What are the two unknowns? One is mass flux is not known, right. Of course, you do not know the temperature, but we will see how to, and we will also the flame thickness, this is flame thickness is not known. It is similar to your boundary layer theory, and where you can basically two unknown and 4 boundary conditions has to be satisfied, and it is a eigenvalue problem. So, you can look at this eigen values are m dot double dash and delta is the flame thickness, right. and we will be looking at basically solving this equation. Either we can use a linear velocity profile and then try to solve it, and considering the physical phenomena into consideration, right. Because we have seen that in the preheat zone there is not much reaction is taking place, that means there is not much heat release is occurring. Whereas in the reaction zone we will have to also use some approximations, that is the convection will not be very much predominant, right. If you look at, I take this as a ignition temperature, right, T ignition, and this is my x, this is basically minus infinity, this is x is equal to plus infinity, and this point is T ignition, and this is your Tf, this is your Tu. Before venturing into that, what I will consider, like let us look at this term, how to handle these terms, right. And for that we will consider the single step chemistry model. F reacting with new moles of 1 moles of fuel reacting with new moles of oxidizer getting into new plus 1 moles of product. And by this what you call law of mass action, we know F is equal to triple dash oxidizer divided by nu is equal to minus m dot triple dash product nu plus 1. This I can call it as a equation 7, I can say 9, right. So, now let us look at this term m dot triple dash I h f I naught is equal to triple dash f h f f oxidizer h f oxidizer plus triple dash product h f product. Now, I will just substitute these values as, I will use this equation 9, I can write down f h f f, there is no problem, but here I will substitute, that is nu m dot triple dash f, right, h f oxidizer plus product wise I will this will be basically minus triple dash f nu plus 1 h f product naught. Are you getting my point? Okay. So, just I am using equation 9 for each of the mass consumption of oxidizer per unit volume in terms of mass consumption of fuel per unit volume, right. So, I can write down this as f as h, I can basically I can write down this as product minus h f f naught minus nu h f, oh no, nu h f right. So, this minus I have taken. and this is nothing but your, I can say, delta H R, isn't it? I can write down that as triple dash F into delta SC, because heat of reaction for the exothermic will be negative. So, negative negative positive. So, this is a heat of combustion. Are you getting? I can write down that. So, now for the, we will be considering this equation 6, right. For the preheat zone, if you look at, this is basically, I can say, this is my heat release rate, and this zone I am considering as my preheat zone, and this portion I can consider as my reaction zone, right. So, for preheat zone, what we will consider? For preheat zone, the heat release is very low, right. That means this term m dot triple dash, sorry, the heat release rate is very 0, very small. That means F delta S C is approximately equal to 0. It is not 0, it is approximately equal to 0. That means we are considering to be 0. So, as a result, what you will get? You will get a relationship, that means this will be 0 in this case. So, I will get equation 6 becomes Cp dt by dx is equal to Kg dt by dx square, right, because this term is 0. Now, I will have to solve this thing. What are the boundary condition here? The boundary condition is x minus infinity dt by dx is equal to 0 and T is equal to T u, and x is equal to x ignition, this is the one, T is equal to T ignition. Are you getting? T ignition. So, if I integrate this equation, let us say this is 10, equation 10, what I will get? I will get that this basically I will integrate this equation and applying boundary condition, we can have Cp T ignition minus T u left hand side, right. I will, what I will do? I will say dx here, integrate it, right, and this will be from T ignition to T u, and this is also you can say that dt dx ignition to dt by dx is equal to minus infinity. So, that will be equal to Kg, Kg is a constant property. So, dt by dx is ignition minus Kg dt by dx at x is equal to minus infinity, this is 0. So, therefore, I am getting dt by dx ignition is equal to m dot Cp by kg T ignition minus T u. So, we are getting an expression for this the preheat zone, and we will stop over here, and in the next lecture we will be discussing about rest of the derivation for getting the laminar burning velocity. Okay, thank you.